All right, everyone, welcome to ECE 5307. I'm Professor Schneider, the instructor. So what I'm going to do today is I'm going to go through the syllabus, which is mostly in these slides, and then I'll go through another set of slides that gives you an overview of what the course is going to be about. So as I mentioned, I'm going to be teaching the course. I'm going to have office hours on Zoom, Thursdays 10 to noon, and there is a TA, Hytham, and he's going to be grading the labs, and he's going to hold a bunch of different office hours. This is all in the syllabus, and these notes are also online, posted on GitHub. By the way, everything you see here that is green is a hyperlink, so throughout the course there's going to be a lot of hyperlinks you can click on with additional information. In terms of what we're going to do in this course at a very high level, we want to understand what machine learning is. In this course, we'll be talking about regression, classification, generation, clustering, dimensionality reduction, maybe a few other things. We want to understand the math behind the standard methods. That's going to involve a lot of linear algebra, probability, and statistics. And then we're going to want to gain experience with standard coding tools, in particular Python-based tools like NumPy, scikit-learn, Jupyter, PyTorch, GitHub, and so on. In terms of prerequisites, if you're an undergrad, you're limited to ECE, but if you're a grad student, you can come from different majors. Topically, the prerequisites are calculus and linear algebra. So if you've taken that at OSU, that would be like these math courses. We're going to be reviewing this material on Wednesday, and there's going to be a practice homework as well as kind of a short exam that's coming up pretty soon on this. And then later in the course, we're going to get more into probability and statistics. I'm going to review that when we need it. It's not really very complicated stuff, but just sort of basics is all we need. And then you're expected to have some kind of programming background, scientific programming. We're going to be using Python, but there's no expectation that you already know Python. If you know something like C or MATLAB, it's very easy to learn Python. So you'll just learn it by essentially doing the labs, looking at examples. So this is an in-person course. I'm going to lecture here in this room, Monday, Wednesday, Friday. I'm going to check attendance randomly. I'm going to have a list of your names, and I'm just going to randomly ask questions. And if you're here, when I call your name, I'll just, say, I'll make a note that you're here. If not, I'll make a note that you weren't here. I'm going to post lecture PDFs like this one in advance. And some of those will have a lot of blanks in the PDFs, and so you're supposed to fill in those blanks. That is in part to keep you guys focused, because if all you're doing is staring at the screen, it's very easy for your mind to wander. You have to be active when you take a class or listen to a lecture, otherwise you're not really going to take it in. So that's why I suggest printing out the PDF in advance, or maybe you can have it on a tablet and then make notes during class. I shouldn't be seeing you guys just sitting there staring at the slides. You should be taking notes. I also shouldn't be seeing you guys scrolling on your phones or doing work for other classes on your laptops, because that's a waste of your time. If you want to do that, just don't come to class. Just do that somewhere else. Okay, so if I see a lot of people doing that, I'll just stop class and ask you to put down your devices. All right. If a lecture is canceled because of weather or something like that, we'll use Zoom, but otherwise we will not use Zoom. I will try to record these lectures and post them on YouTube if you want to see them later. But sometimes YouTube doesn't work out. Sometimes there's a problem with the recording, so you shouldn't rely on that. In terms of questions you might have on homework, on lecture topics, on the labs, I don't want you to email me or email the TA. I want you to write your question down in a Carmen Canvas discussion. So So right now, there's many discussions that are set up in advance. And the reason why we don't want you to email us is because many of you guys might have exactly the same question. And if you email us, it might take us a long time to get back to you. But if you post a discussion, then all of you guys are able to answer those questions because you might have had exactly the same issue with your lab. You might know the answer. So you are encouraged as students to go and interact with those discussions and answer the questions that are posted there as well. Okay? So if you send us an email, we might be like, hey, could you just please post that to the discussion forums? And don't be offended. And then we'll answer it there. Okay. For grading, there's several components to the course. There's going to be weekly homeworks, although these are not going to count directly for a grade. There's going to be weekly coding labs, 15% of your grade. There are going to be 4 different midterm exams. The first one is going to be just a half a period, like 25-minute exam, so that's worth a little bit less than the others. The dates of the midterms are set, so don't come to me later in the course and say, oh, I didn't realize we had a midterm that date, and so I planned a family vacation, and our whole family is going to be away that week, so sorry, I can't take the midterm. So now that you know that the midterm dates are like this, you can negotiate with your family and choose another week. Now, of course, if you would rather go on a family vacation and miss the midterm, you're welcome to do that, but it will probably affect your grade. So it's up to you. There's going to be a final project worth 25% of your grade, and there's going to be a small attendance participation, 5%. So as I said before, the homework, there will be assignments and solutions posted, but not graded. Really, the point of the homework is just to practice. If all you do is listen or watch the lectures, you're probably not going to be able to understand the material. You have to interact with it. And the homework gives you a really good way to do that, especially if you want to do well in midterms, because the midterms are going to be sort of math focused. So the homework problems are very similar to the midterm problems. The labs are very different. It's very useful to program and code machine learning. That's definitely a big part of that course, of this course, but it's not going to help you do well on an exam. The exams are not going to cover coding at all. So being a great coder is not going to help you on the exams. That's what the homework is for. The final letter grade will be curved. So sometimes usually the averages on my exams are kind of low. Don't let that stress you out. As an undergrad, you're going to get one curve. Grad students will get a different curve. For the undergrads, I try to curve so that roughly 1/3 of the course of the students get A's, 1/3 get B's, 1/3 get C's. But if you're falling behind your rest of your peers, you could get a D, you could get an F. That happens. But I try to avoid that. The grad students would try to give half A's and half B's. But that's just roughly speaking. Okay. Any questions on any of the grading stuff or anything I've discussed so far? Okay. Final project is the goal is to apply the machine learning concepts you've learned in this class to some data set that I'll give you with some design objective. It might be regression, it might be classification, something like that. And there's going to be, how many of you guys know what Kaggle is? Okay, Kaggle is a website that hosts a lot of machine learning competitions. We're going to make a private competition just restricted to this class where you guys are going to compete with each other for this project. And what I found is it makes it a lot more fun. People really get into the competition aspect of it. The projects are going to be done on 3-person teams, but the project is structured in such a way that you can collaborate with your teammates closely, or you can work completely by yourself if you prefer. So it gives you the opportunity, but you don't have to take it. We'll talk more about the project details later. And for your team, you can choose your partners, or if you feel like you don't know people in this class, that's fine. We'll put a team together for you. And the deliverables for the project are your Python code and a written report in PDF that describes everything you did, why you did it, showing evidence, graphs, I'm trying to understand your reasoning, trying to understand what you learned in this class, how much you learned, how well you learned it. But we'll get into all those details a bit later in the term. There are some textbooks if you're looking for some, but these are all optional. The first two are the first and last are free. The middle one is a soft cover. It's relatively cheap if you want to buy it. I'm sure you could find a PDF out there as well. But these are just totally optional. Otherwise, I'll just be providing you with PDF notes that contain everything you need to do, everything you need to learn to do well in the course. So in terms of distributing the materials, I'm going to be using a combination of Carmen Canvas and GitHub. So for Canvas, we'll use a lot of its great features like announcements, discussion boards. I'll be posting the homework, the solutions there, posting links to the GitHub labs, exam solutions, final project details, grades, all that stuff. But Carmen doesn't really work well for code. So for code, we have to use GitHub. I'll also be putting the lecture PDFs there, all the demonstration code. The labs will be done through GitHub. Basically, the way the lab works is you will each have a private GitHub repository for that lab, for each lab, constructed for you. In that repository, there will be a Jupyter notebook, which will have a bunch of cells with instructions of what to do. And you just have to fill in each of those cells, and then you push it back up to the cloud, and it gets graded. We'll be talking about Jupyter notebooks in a second, so you'll see an example of what one of those might look like. But that's basically how the labs work. Any questions on the labs? So you guys will be doing your labs on your own time. There's no particular time you need to do it or room you do it in. It's just you can do it on your own laptop. You can do it in a computer lab, however you prefer. You won't need really high performance machines for it. All the data sets in the labs will be small, so you can run them on laptops, that's fine. You can run them either in the cloud using Google Colab, or you can run them natively using the Python on your local machine. Those are both options. All those things are described in a bunch of files that I've posted on GitHub. And the final project will be kind of similar. It will be also done through GitHub, except you'll have a group repository where the 3 members of your team will all have access and can all collaborate on those files. So in terms of GitHub, everything is located in this repository. And this is a private repository. So to get access to it, you need to follow some instructions that were posted this morning in a Carmen Canvas announcement. There's a couple steps, but it's not too difficult. And once you have access, you'll see what has been posted there. And I will be regularly posting more and more stuff there as we go through the term. Right now, for sure, these slides are posted, and the ones later today. I don't think I posted Wednesday's lecture slides yet, but I'll get that done soon. If you use a web browser to look at this directory, you will be able to view those PDFs and the Jupyter notebooks. It doesn't work super well, though, because with a PDF, you can see the first few pages on GitHub, but then if it's longer, like if the lecture slides are 30 pages or something and you want to see towards the end, it makes it difficult for you. So really, the way you usually work with GitHub is you pull down a copy of that repository from the cloud onto your local machine. And then you have a copy, and then you can access all the PDFs. You can run the Jupyter notebooks, you can run the code and all that natively. And then since I'll be regularly updating that main repository, you will be regularly pulling down new versions and updating your local files. So that's the usual way you deal with GitHub. How many of you guys have heard of GitHub? Great. How many of you guys have worked with GitHub? Okay, excellent. Most of you. All right. And as I said before, you can run Python natively or you can run in the cloud. I think it's a little bit more complicated to use Google Colab than it is just natively personally, but if you have a really old machine or something like that, then maybe you do want to run it in the cloud. I'm not sure. It's really up to you. You can try both. Okay, we're going to be using Python because basically it's a very general, very powerful language. It is the language for machine learning, deep learning, all that stuff. It's free, it's open source, unlike MATLAB. It has a lot fewer bugs than MATLAB. Like I said, no Python background is expected. We'll teach you. It's very similar to C or to MATLAB. And if you'd like to get a head start, there are tutorials in that primary course repository on Python, and NumPy is like the numerical package for Python. There's some links I posted if you're really comfortable with MATLAB and you want to know like how to go from MATLAB to Python. I posted a few links there, and I posted some practice materials if you want to get into that. It's totally optional though, it's up to you. And I mentioned these Jupyter Notebook demos. They're one of the most friendly ways to run Python code, especially if you're just playing with things and developing things. And basically, these Jupyter Notebook files, they have an extension .ipynb, and they are a combination of text and hyperlinks and code and plots. And typically, when you see one of these, it has already been run. And so the code in this block has run and it has output this. And then the code in this block ran and output this and so on. But if you want to rerun the code yourself, you have a copy of this locally and you have Python installed, you can just go through and you can run block by block. You can make changes to see what happens and so on. And so this is what the labs will look like. You'll have some blocks with some instructions, and you basically have to fill in what's missing in each block. All right, any questions on anything I've described so far? Okay. All right, so just some warnings. This is not an easy course. A lot of undergrads tell me at the end of the semester this is the hardest course they've taken at OSU. So if you were just looking for like a relaxed course in your last semester here, it's probably not going to be that. So I want to be clear up front about that. There's a lot of linear algebra, probability. There's a lot of math. Weekly homework, as I mentioned before, is going to be important to really understand things, but it's going to take some self-discipline to do it. I wasn't able to find a grader, so that's why there's no grading of it, but it doesn't make it unimportant. In terms of background, linear algebra is super important. It's basically the language I'm going to use to talk about machine learning. So if you don't understand linear algebra, it's going to be very difficult to understand what I'm saying. It's also the main reason that students drop this course, is they get to a certain point and they're just like, I have no idea what's going on because my linear algebra is really weak and I just don't know. Again, you'll get a chance to review and practice your linear algebra in homework 1, and so I suggest to take it seriously. Yes?
Other than homework 1, do you have any like suggestions for things to like practice linear algebra?
It's hard to say because, you know, like you'll find a whole book on linear algebra, right? We're only going to be using what's like in the first chapter of most linear algebra books. We're using really elementary stuff, but you need to know it well.
Yeah.
So like, for example, like matrix multiplication, like that should be something that gets hard-coded in your brain so you don't have to like go back and look up, wait, what do I do again? Because we're going to just like, you're going to see it and you're going to have to understand what that means. Things like that. So the homework problems just give you examples of what I'll talk about. I don't know of like, I've looked, but I haven't found like examples of exactly what we're doing. A lot of linear algebra courses go a lot deeper than what we need. We don't really need much, but I need you to understand and be fluent with the basics, basically.
Thank you.
Sure. Any other questions? Okay. As I mentioned before, it's really important in any course, really, take an active approach to doing it, to attending that course, taking notes and so on. I think with the way the human brain works, there's different inputs. There's your eyes, there's your ears, there's different parts of the brain. Information needs to kind of flow through your brain. When you write something down that you're listening to, it forces that content to go through different parts of your brain and interact and get stored a different way than if you're just sitting there and not writing anything down. So I think it's super important. Like when I attend a meeting, like a research meeting, even though if I never look at the notes later, I will just be writing down and summarizing, okay, this is what's going on now, because it forces me sometimes to say, okay, what is going on right now? What are we actually talking about? But if you go through that process of writing it down, it kind of codifies it in a certain way that is more than just sitting and listening passively. So I suggest to do that. I suggest to be writing in the margins of your notes. Maybe I said something that's not exactly in the notes, but it's kind of important, or maybe I assumed everyone knew that, but you didn't know it, and so good idea to write that down. Again, don't get distracted by your phone or your computer. I know how easy that is, but it just removes you from that active participation. And finally, don't cheat. Don't copy things. Don't, during the exams, don't look over and copy your neighbor's solutions. I'm obligated to report cheating. All faculty are. I definitely have done a lot of that in the past. I don't like doing it, but so don't do it. Any questions on anything? Okay, everybody good? No questions on anything? Syllabus? Yes.
For the competition, is our grade based on how well we do in the competition compared to everybody else, or?
For the final project, your grade, I'll share a rubric later, but it has like, the project report is usually about worth half of your final project grade, and even within that report, I'm looking for various things. Part of your project grade is how well you did in the competition, but I think I do it in a pretty fair way, or like if two people are like number one and number two, but like their scores are almost identical, like they will get the same grade. So, but if one person or one team is like really far away from everyone else, yeah, they may get a much lower grade for that reason.
Thank you.
Yeah. Okay, any other questions? Yes.
Is there a reason why undergrad and grad students have a different grading curve?
Yeah, because performance in these classes has a lot to do with mathematical maturity. So when I was, this is like my 26th year here at OSU. When I was younger faculty, I would, for 10 or 15 years, I used the same curve for everyone because I thought somehow that was more fair. But what I saw, looking at the same person as they went through, maybe I would know them as an undergrad, and then I would see them progress all the way through PhD, the same person with the same intellect, if they took a given course, as a senior, they would get a much lower grade than if they took it their second year of grad school because they've had so much practice with related material. And so I think really it's just different. So I've taught this course 10 times now. And when I look at the histograms at the end, the grad students are just, as a pack, doing much better than the undergrads. So it's never that the grad student curve is easier than the undergrad curve. It's always equal or harder, usually harder. Even though I try to get A's and B's, no C's for the grad students. Because as a grad student, if you get a C, you're on academic probation. As an undergrad, that's not the case. A lot of undergrads have a C average. You know. So yeah, that's a bit why there's different curves and why the curves are constructed the way they are. Okay, all right, any other questions? Great, okay, so let's move on to talk a little bit about what this course contains. So first of all, what is machine learning? Machine learning is really a whole bunch of different things. We'll zoom into a few different, what we call tasks in machine learning. These are sort of the objectives, what you're trying to do. So first, we'll talk about regression, and this is actually what we'll do first in the course as well. Regression, which is basically predicting a numerical value or, you know, a bunch of numerical values. Then classification is similar. You're also predicting something, but rather than a numerical value, you're predicting a category, something that can't really be coded as a number. And then we'll talk about generation, which is basically generating synthetic data. This could be like large language models. They try to synthetically generate text. A lot of image models will try to synthetically generate images. You can kind of synthetically generate any kind of data you want with the right training and the right model. Clustering is if someone gives you a data set and asks, can you partition this data set into different categories? That within each category, things are similar to each other, but then across categories, they're different. So you're kind of trying to figure out the categories that you might use for classification when you don't even know them yet. And then compression, as you're all familiar with, is basically squeezing data in some way. So, you know, MP3, JPEG, things like that, squeeze audio files, images. But there's other reasons you might want to compress data. You might want to compress it to 2 or 3 dimensions just so as a human you can visualize it and understand it visually. Okay, so let's zoom into a few of these. So starting with the first task, regression. Just as one example, maybe what we want to do is we want to use current and past data to predict the stock price in the future. So what kind of data might we want to use to do this? Does anybody have any ideas? Don't be shy. Yep. Financial data, right? Like maybe this stock's price in the past. What about other? Is that all we're limited to?
Overall market trends.
Market trends, yeah.
Similar stock prices.
Yeah, other stock prices. What else?
PE ratios.
Statistics computed from stocks. What else?
I was gonna say general public perception as a metric of some sort.
Yeah. What about even just like news articles and so on, right? So, you know, 20 years ago, that might have been sort of difficult. How do you turn a news article into a number that would be useful to predict the stock? Well, these days with large language models, that's not so difficult anymore. So anyway, you can imagine there's tons of kinds of data you could use for prediction, and that's the point. Next, how do we actually do it? So in the old days, you know, especially 50 years ago, what you would definitely do is you would take some courses in economics, you would read some books, read some journal articles, you know, talk to some economists, and you come up with some theory, some mathematical equation where you plug in certain numbers and out come other predictions. But as you can imagine, that's quite hard to do with the stock market. There's no real theory that predicts very closely what's going to happen. So instead, we could use a learning-based approach, and that's what machine learning is. You basically collect a whole bunch of data of what happened in the past. If I go back a month and I had this data, now, because it's a month ago, I know exactly what happened. If I go back 3 weeks ago with the data, I know what happened then, and so on and so on. And so you can build this data set that says, given at a certain time this data, this is what actually did happen. You can try to learn the connections between the data you're using for prediction and the thing you're trying to predict. And this actually is done quite a bit today. There's a lot of ECEs as well as other majors that are hired by financial firms to do exactly this, to develop algorithms to predict, stocks and other financial quantities. Okay, so at a high level, the goal of regression is to predict some numerical value or values given measurements of related quantities. All right, any questions on regression? Okay, so let's now talk about classification. I made a slight update to the notes just a few minutes before class, so if you see a different image here, that's why. Basically, in classification, we also want to do prediction, but instead of predicting a number, which is, a number is basically a value where you know, if I give you two numbers, you immediately know one is larger than another. There's an ordinal relationship between numbers. Sometimes we're talking about things like categories that have no, like if I say, is the letter A, better than the letter C? You'd be like, well, I don't know what you're talking about. There's no better. They're just different. There's A, you use it for something, and C, use it for something else. So those are categories. So in classification, what you do is you predict a category. And so as an example, you might be given a little image, that little image, and you are asked to predict what is the letter that someone wrote in that image. And if you have some data that tells you, well, this is actually a lowercase h, and this is a lowercase b, and so on, you can train a model that takes in one of these little images and does its best to output the letter that was intended to be there. Here again, like if you tried to do this in the old-fashioned way where you come up with some mathematical model, it's a little bit difficult if you think about it. Like what exactly makes one letter different from another letter? Because there's a lot of freedom in how people write these letters, and sometimes you see, one person's U might be another person's 9, something. So it's hard to say exactly what the equation is, but we as humans, we can do this, right? We've seen so many examples of these letters that we've figured it out, or we have a pretty good ability to guess. Okay, so this is the task of classification. Predicting some category given measurements of related quantities. Any questions? Okay, so we'll talk about this in the course after we talk about regression. Generation is basically synthesizing data. So maybe our objective is to generate random images of cats. This is something we can do. Given enough images of cats, we can train a model to just generate new ones it's never seen before that are plausibly, to us humans, cats. It's pretty cool, but it's what these modern methods can do very well. It doesn't have to be images. It could be audio. It could be video. It could be music. Just recently, the #1 song on the country charts was completely written with AI. All the sounds, all the the music, everything. I don't think it was very good, but you can do it. I guess a lot of people thought it was good enough to make it to #1. Okay, any questions about generation? Okay, we'll talk about that later. Towards the end of the semester, we'll get into a few other tasks like clustering, forming categories. So one could be like the following. I give you a whole collection of text documents. I don't tell you what's in them, and I want you to categorize them like, oh, these are sports articles, these are about politics, this is about religion, this is like a for sale ad. And it doesn't know any of those categories in advance. It basically just comes up with a bucket. Well, these are all similar to each other, but kind of different from other things. And these are all similar to each other and different from the other things, and so on. So Clustering is sort of like categorization. In some cases, this is just a two-dimensional data set where each data point is just two numbers. As a human, we could probably do a pretty good job of clustering this. I would say, well, this is probably one category, this is probably another, this is another, this is another. How we handle this point, have to make a decision. You know, maybe we say, that's not really part of any category, that's an outlier, if we have a model that can do that. Otherwise, if not, we might say, well, I think that that's probably part of this, and so on. Of course, it gets more difficult as we get into higher dimensions, but modern methods can cluster very well. Any questions? Yes.
What's the difference between clustering and classification?
Great question. What's the difference between clustering and classification? So in clustering, what I give you is I give you the data to use for prediction and nothing else. In classification, I give you the data I use for prediction, but I also tell you, here are the categories that I want you to use for prediction. Like, it has to be a cat, a dog, or an elephant, right? And tell me which of those three it is. Here, I just give you a bunch of images and I say, what are these? Can you tell me which ones are similar to each other and put them together and then make another category of these ones that are similar to each other and so on.
Clustering would find patterns between
Yeah, they both find, so in the first case, in classification, you find like a pattern between the prediction and the target. Sort of, it's a pattern between those. In clustering, it's just patterns in the prediction data, period. Yes?
Is generation fundamentally different from just like pure classification or progression?
So, I mean, there's connections between all of them, but so again, there's a distinction between what people call supervised and unsupervised machine learning. In supervised learning, what you're given is you're given things you use for prediction and targets. And you're given a whole bunch of examples of those pairs. And then when it comes to actually applying the model, you're just given the thing you use for prediction, and you don't know what the answer is. You don't know what the target is. So those are supervisors when you have those two things, the kind of input-output together. And then unsupervised, you have no target, you just have data. So in clustering, I just have, in this case, like lists of pairs of numbers. That's my data, nothing else. For generation, I might want to generate more points from this distribution. So the input would be the same. I would give it that list of two-dimensional numbers, and I'd say, generate some more. And maybe it would put one here, and then another one here, and another one here, and so on. So there's no targets here either. But another option is that I would have given you labels. So I might say, these are all the red points, these are all the blue points, these are the green points, and the purple points. Now I've turned it into a classification problem. Now, when I say there's going to be a new point over here, is that a red point, a blue point, green, or purple point? And you'd say, oh, it's a red point, probably, right? So that's now become a classification problem. But if I don't have any of those labels, then it's just a clustering problem. Or generation, unsupervised. Okay. Great. Any other questions? Excellent. So compression or squeezing data. So as I mentioned, there's many reasons why you might want to do this. Like, if we were not able to compress audio and image and video data, then it would quickly consume the available storage on our mobile devices, our hard drives, and all that. Audio files, you can safely compress them by about a factor of 10 without really hearing much difference. Video, even much more than that. So just for the purpose of like storing and transmitting data, it's often important or really useful to compress it. But maybe we, like I mentioned, maybe we want to somehow visualize our data as humans. Someone gave us a whole bunch of data, and just as a human, we have a lot of intuition, and we're pretty good at noticing patterns. So we might want to take that high-dimensional data and convert it into something we can look at, make a picture of it. So there's a lot of different methods to do that. PCA is one of the classical methods, but there's some other ones we'll talk about. And so those are all compression. And yeah, so in terms of compressing images, here, maybe this image here, I'm pretty sure I got that in some kind of compressed form when making these notes. And it probably used some, I don't know, could be JPEG, some kind of image compression standard that was developed, most of them were developed in the 80s. And, but nowadays, now we have a lot more computing power, a lot more people have thought about how to do this, and we might say, okay, what if I want to compress even better than JPEG? And what if I know that the thing I'm compressing is going to be images of plants? Well, now I have kind of an easier problem. I don't have to compress all images of everything. I know they're always going to be plants. So that's going to give me an edge. It's going to be able to let me do a little bit better. So I would be able to train a model that's going to work better than JPEG for at least that specific subproblem. Okay. Sometimes the compression needs to be lossless, which means you haven't lost anything at all. There are a few algorithms to do that, but those were almost all developed, I don't know, many decades ago. And you can compress, depending on the source, maybe by a factor of 2 or 3, depending on the source. But to compress a lot more, you have to allow error into the process. So all your audio, video, image coding standards, they're not perfect. They lose data. But the data they lose has been very carefully constructed so that the human brain audio-visual system can't see it. So they're very clever in how they remove 90% of the data, but they rely on the fact that humans tend to only see or hear this 10% of it. Everything else is kind of invisible to us. So that's how they work. But if you actually looked at the distortion, you compressed and recovered and you compared it to the original, it would be different, definitely. Okay, so those are basically some examples of tasks. Any other questions on any of these things we've talked about so far? Okay. So how do we do this then? So as we saw before, the traditional approach is to obtain a model from some scientific expert and then apply that model to a given task. And sometimes this is a great idea. For example, if you're doing circuit design, there's a few equations that work really well for circuit design, Ohm's law and various other ones, and you're almost kind of crazy not to use them. Like, why wouldn't you use them? That's how they work. But sometimes, we don't have that model. Like we talked about the stock market. We don't really have Ohm's law for the stock market. So that's one reason why you might need to learn instead of go to an expert. Or another example is, well, there might be a good scientific model, physics model or something, but in order to use it, you have to know a lot of things you don't know. So for example, acoustics is pretty well understood subject. There's great acoustical models. I could predict for you all the echoes you'd be hearing from my voice based on bouncing off the walls, the ceilings, the desks. It's going to be absorbed in different ways, depending on how many of you are seated here and where you're sitting and so on. That can all be predicted. But if you want to do something like echo cancellation in the back of the room, in order to use that model, you would need to know all those parameters. You need to have this perfect model of the room, architectural model. You need to know all the acoustic coefficients of all the different surfaces. You need to know where all the people are, how many are there, and so on and so on. So you just can't really use that scientific model. So instead, if you have something like noise canceling headphones. It's basically learning what's happening on the fly at the location where you're using it, and it's just figuring out how do I cancel out the noise. Okay, so those are examples, you could say examples of machine learning. Okay, so we basically learn a model based on many examples of data that we have. So in terms of the math, we'll start to now put some mathematical notation down. There's basically 4 key ingredients of what you need to do machine learning. You need a modeling function. We'll call this f sub theta. That depends on some adjustable parameters. So this is the function that inputs the data you're using for prediction. And that model depends on these parameters. Theta, here we're saying that there are d real numbers. And essentially the purpose of training your model is to figure out how to adjust those parameters. There could be hundreds of billions of those parameters. There could be 2. It just depends on what you're working with. The next key ingredient is a loss function. This is something that tells us how well a given model is performing. Is it predicting the data really well, or is it not predicting the data well at all? And what do we mean by well exactly? So we'll talk about different ways to construct loss functions and the implications of those choices. Then, in order to adjust these parameters, we need a training data set. We need many examples of the kind of things we'll be doing. So if I'm doing supervised machine learning, I need many examples of the things I'm using for prediction and the targets I'm trying to predict. If I'm doing unsupervised learning, I just need many examples of the things I'm using for prediction. And finally, we need an optimization algorithm that basically figures out how to use this training data and that loss function and the modeling functions architecture to adjust those parameters theta. And in particular, what it tries to do is it tries to find some combination of parameters theta that makes the loss small on the training data set. In doing that, our goal is really not only that it works well on our training data set, our goal is really that it works well on unseen test data that I don't have at the time of training, but I will eventually want to use this thing in the wild, and that's really what needs to work well. Who cares if it works well on my training data if it doesn't actually work well in practice? Okay, so in order for this to happen, we'll learn all about things like overfitting, model order selection, feature selection, things like that, that tell us how to carefully design our modeling function, how to carefully design our loss, and how to design our optimization algorithm so that this happens. Okay, any questions so far? Okay. I'll just give you one page of a little bit more in-depth explanation. If this looks really intense right now, don't worry about it. We're going to be going through this over the next few weeks. At some point, when you look at this, this should look very natural. You should be like, yeah, of course. But even if now it doesn't look like that, that's fine. So let's again saying we're doing stock market prediction. Let's call the future stock price that we're trying to predict Y. This is just going to be a real number. And let's say maybe we're using past stock prices. And we'll just say we have D of those prices. We'll stack them into a vector boldface X, real vector with D numbers in it. And so our modeling function is going to take in one of these X vectors, and it's going to output an estimate of that stock price Y. We'll call that estimate Y hat. Now, it's not going to be perfect, so it's not going to equal Y, but hopefully it's close. In terms of what that function looks like, there's many options. We'll talk about linear functions first. We'll talk about tree-based functions. We'll talk about neural networks. Many choices there. And then we need a loss function that tells us how well we're doing in order to guide our training to improve the parameters theta. So if y hat is our current prediction from x, and y is the truth, which we know because we're training the data, one option would be to make the loss function the squared difference between y and y hat. But that's not the only thing you could do. You could actually use the absolute difference between y and y hat. And these different choices have a lot of ramifications in what happens, what you learn, how well it works, how easy it is to compute theta. And we'll get into all those details. In order to do that training, we're going to have a data set, which is going to be a whole bunch of XY pairs. Here we're indexing using I, and there's going to be n pairs in total. And the optimization algorithm tries to solve this mathematical problem. This is so in this course, or in math in general, if you say the minimum of something, it tells you the smallest value that the function can take. If you say argmin, it tells you the location at which that minimum happens. So this argmin means the value of theta that minimizes this expression. What is this expression? It's an average over all our training indices of the loss function on the ith target and the prediction of, the prediction from the ith set of input data, which we call y hat I. So maybe this is like the square difference between yi and y hat I, and this is averaged over all our training examples. And we want to somehow choose the theta that minimizes this average. And that theta we will call theta hat. And once I have that theta hat, now I have this learned model, f sub theta hat. Now I can bring that out into the wild, and I can plug in a new x, which I don't know the y it corresponds to, and I can give you my best guess of that. Okay, so any questions on this? Okay, again, if this looks very intense, don't worry about it. We'll get into all these details later. All right. So what we'll learn in this course is we'll learn different ways to design that modeling function, linear, polynomial, neural networks, trees, different ways to design the loss function using some statistical frameworks like maximum likelihood, MAP. Actually, I don't think we're going to do much with kernels this term. We're going to construct algorithms to optimize theta, stochastic gradient descent. I may take out the Armijo stuff. For various tasks: regression, classification, text generation, clustering, dimensionality reduction. In order to do this well, we're going to have to learn some other important topics like generalization, regularization, ensembling, and some important methods like PCA, non-negative matrix factorization, Gaussian mixture models, expectation maximization, and so on. So what you'll need to do this, our main goals: learn the concepts and the math behind machine learning, but also equally important is to learn how to implement this stuff using standard software tools, Python-based tools. To do this, we got to start with undergrad level linear algebra, undergrad level statistics, probability, some scientific coding. And we'll talk about linear algebra more next on Wednesday in a couple days. If you guys have any questions, please come see me after class. Otherwise, I'll see you guys on Wednesday.